Hello, folks. Sorry I couldn't be there with you today, but we're still going to get our class time in, so don't worry about that. So, the videos and readings that you had were concerning nutrient cycling and the soil ecosystem. And this, lecture that I'm going to give here is going to talk a little bit more about some of the things that you were introduced to in the readings and the uh, lecture video that you watched in preparation for this. And so, I want you to be able to look at these vocab words. We might not necessarily cover them all today, but take a good look at them. Pause the video if you want, but be able to define these in one or two sentences. These are basic terms that we're going to be using throughout the course, and so you should be able to use these terms with relative regularity. So, in this lecture, we're going to basically talk about how soils are an ecosystem made up of things like nutrients, microbes, organic matter, all the way up to things like centipedes and earthworms. And these ecosystems are shaped by both biotic, so biological forces, and also abiotic, things that aren't biological, things like pH and rainfall. And we're also going to consider, as we sort of build towards understanding the plant, talk about some of the macro and micronutrients that plants need in order to grow. So, what do plants need? First off, they need carbon. They need to make carbohydrates through photosynthesis. And in order to undergo photosynthesis, plants need light and air. So plants basically use light as a fuel to pull carbon out of the air in the form of carbon dioxide, and they use this carbon to build both their structures but also to build starches that they then eat themselves. And we also like to eat these starches. So the starches you find in a carrot or a stalk of celery, that's the carbon that the plant has brought out of the atmosphere and fixed into biomass. So, in order to do this, plants need macronutrients. And so, macronutrients are nutrients that plants need a lot of, and micronutrients are things that plants need small amounts of. And so, the main macronutrients that we're going to continue talking about, which we have been earlier in the course, are nitrogen and phosphorus. But notice that there are a whole bunch of other macronutrients as well, notably potassium. And so most fertilizers will have nitrogen, phosphorus, and potassium in them. There's also a bunch of micronutrients, which we won't really talk about much today. But these are, while they only need them in small amounts, they are just as necessary as the macronutrients. Plants also need water, but you can of course drown a plant, and so if the soil is set up such that water is not allowed to drain away from the plant roots, that they stay surrounded in water and there's no air in the pore spaces around the plant roots, then you can drown your plant, because the mitochondria inside the plant need access to oxygen to respire. And so without access to oxygen, the plants drown and they die. And we also need quality soil, and we're going to spend a lot of time talking about what quality soil actually means. So this is what plants need in order to grow. So with soil quality, there's three basic components. There's biological, chemical, and physical. And so chemical is just dealing with the types of elements that are in the types of elements and compounds, molecules that are in the actual soil. So nitrogen and phosphorus is dealing with the chemical aspect of the soil. There are other elements that are important that we'll talk about. Biological is that soil ecosystem, everything from the microbes and nitrogen fixers all the way up to the centipedes and earthworms. We'll talk about that too. and physical. So that's the actual makeup of the soil. And my wife Ruth will be coming in next class, and she'll actually cover a lot of what there is to cover about the physical parts of the soil quality. So I'll cover it just briefly here, but she'll talk much more about it when she comes in. So, soil physical properties. There's basically a horizon or different horizons that you see in a soil profile. Soil, of course, comes from bedrock, and so bedrock weathers slowly and steadily into soil until you get this nice A horizon. This A horizon is a mixture of this parent material, rock, and the nice leaves and twigs and sticks, the organic matter that forms the humus. Remember, humus is one of our words. And so that organic matter mixes with the parent material, making this nice, rich topsoil. This is actually not quite the scale, not at all, because topsoil is actually extremely thin compared to all the other layers of the soil usually. And so topsoil is very precious, very, very, very precious. And so we want to avoid losing it to erosion. And so Ruth will cover a lot of this, so I won't cover it very much, but if you want to classify soil as either sand, silt, or clay, those are the three end members of soil. And so, but usually soil is a mixture of these three. And so loam is the optimum. Loam is the optimum soil. It's equal parts sand, silt, and clay. But if you have a little more clay, then you end up having clay loam. If you have a little more sand, you end up having sandy loam, more silt, silt loam. So see basically how this triangle works. Sand, silt, and clay are the three components of soil. So that's a soil texture chart. And we want to talk about we want to talk about soil compaction. And so I mentioned that you want to have air next to the roots. You don't want them to drown in water. And so in a normal soil, you have soil particles, and they're far enough apart that you can have water move through, but also have air move through. Now, if the soil gets extremely compacted, this can happen with a lot of tilling and running over the soil with heavy implements. Then soil and water can't flow through. You can end up getting water trapped in these small pores, and you can end up drowning your plant, or water and air can't move through it at all. And so, if water can't move it at all, then you're going to have water pooling on the surface. And the roots also won't be able to penetrate deep down into compacted soil. So, when we're talking about macronutrients, specifically nitrogen and phosphorus, what plants really need are bioavailable nutrients. And so bioavailable nutrients are exactly how you would expect, or are exactly what you would expect them to be. They're nutrients that are actually available to the plant. So in order to understand what bioavailable nutrients are, let's first talk about what makes nutrients non-available. So, for instance, you folks know from talking about the nitrogen cycle that nitrogen in the atmosphere is not available to plants without the help of nitrogen-fixing bacteria, and so it's not biologically available. And we talked about how organisms like nitrogen-fixing bacteria, and also us through the development of inorganic fertilizers, can actually turn this non-bioavailable atmospheric nitrogen into bioavailable nitrogen. And the efficiency of this process can depend on soil quality, things like pore spaces, organic matter, and pesticides, fertilizers, etc. And I should also mention, I forgot to mention that the organic matter, nitrogen in organic matter is not bioavailable. So, the nitrogen in my arm is not available for plants to use. Just like, but now, in dead and decaying organisms, that nitrogen is actually freed up. It's taken out of the organic phase, and into the bioavailable phase. And so decomposers play an important role in releasing these nutrients that are bound in organic matter and releasing them out into the rest of the ecosystem so plants can use them. So phosphorus can also be made non-bioavailable. It can be bound to sediment. We call that being adsorbed. And so if phosphorus is bound to the sediment, then it's not available for plants to take up. And organic matter, again, if it's got phosphorus in it, that phosphorus is not useful for plants until that organic matter is decomposed. And soil pH is really important in determining whether or not phosphorus is bioavailable. At pHs above 7, phosphorus tends to precipitate out of pore water with calcium, and so it becomes unavailable to plants. But if pH is below 6, then phosphorus starts to bind with aluminum and iron. So when it binds with aluminum and iron in the soil, it is not biologically available to plants. So the optimum pH, soil pH, in order for phosphorus to be widely available is usually between 6 and 7. You can go outside of that range a bit and be okay, but you're starting to lose some of your phosphorus. And so actual nutrient loss completely out of the system can happen in a number of ways. Leaching is when water actually washes the nutrients out. This is a big problem for nitrogen, not so much for phosphorus. Erosion is when the soil particles are physically removed from the system, and so that is actually a pathway through which phosphorus is commonly lost. Volatilization, mainly an issue for nitrogen, when the denitrifying bacteria turn nitrogen into gas. And also, remember, harvest and removal of residues. So if we have a cornfield and we harvest the corn, then the nitrogen and phosphorus that were used in order to grow that corn are now no longer in the field. They've gone out to someone's table somewhere or out to a feedlot. Could be, hundreds and hundreds of miles away. And in the same way, if we grow that corn, we harvest the corn ears, but we also bale up the corn stalks and sell those to someone to feed to their cattle hundreds of miles away. We've removed even more of the nutrients. So it's important to consider your inputs and outputs, just like we talked about the first few days of class. If you bury these nutrients deep enough, they can be taken out of that decomposition cycle that I talked about earlier. And if they become trapped in the non-bioavailable pools that we talked about, just the past couple slides, like organic matter, for example. Now we're going to talk a bit about the soil food web, and that's all the organisms that live within the soil. And we can thank them for actually making nutrients bioavailable again, because once they're taken up by organisms, turned into organic matter, they're no longer bioavailable. And so the soil food web's job is to make these nutrients bioavailable again. So if we start at the top by looking at a tree, a nice tree that's growing, taking in carbon dioxide and taking in sunlight, taking in nutrients, taking in water, producing organic matter. That organic matter falls to the forest floor, and that organic matter looks really yummy for decomposers like fungi and bacteria, these primary consumers. And so just like us, when fungi and bacteria eat something, they take some of that and build their own biomass, and it's used for their own functioning, but they also excrete some of those nutrients in the form of nutrients that other organisms can use. So just like we eat food, use some of it for energy and some of it for growth, and then we pee or poop out the rest as nutrients, fungi and bacteria do the same thing, and so at this level, they're eating the organic matter, using it, but also excreting, and these nutrients are then free to be taken back up by plants. And then, but now you've got nutrients sequestered within these guys. And that's, of course, the secondary consumers can then eat these guys. Same thing happens, nutrient released, and then so on and so forth. These guys eat these guys, nutrient release. So at each one of these steps, each one of these trophic levels, each one of these places where one level of organisms eats the other, nutrients are released and released back into a form that plants can actually use. So that's pretty helpful. And so as you can see, bacteria and fungi are the foundation of the soil ecosystem, pretty important. And we've already gone over the nitrogen cycle a whole bunch, but I just want to remind you that these nitrogen-fixing bacteria are really important for bringing nitrogen out of the atmosphere into the soil, and these decomposers, that once you end up with this organic matter, they're really important in unlocking the nitrogen in this organic matter, making it reavailable for plants to use. So just remember the nitrogen-fixing bacteria and the decomposers and the key roles that they play in releasing nutrients back into the soil for plants to use. So again, we've talked about the phosphorus cycle before, but I wanted to talk to you a little bit more about this. So we have available phosphorus here. That's phosphorus that plants can actually use, and available phosphorus is applied, using fertilizer or cattle manure. And remember, what we have to watch out for is you can get phosphorus adsorbing or sticking to pieces of soil. It's taken out of the available pool if it's sticking to soil. You can also mineralize it, so you can precipitate it out if the pH is appropriate. And so, again, you lose it from the bioavailable pool. Leaching doesn't happen that much, but it can happen a little bit with phosphorus. And again, so you take available phosphorus and microbes, turn it into organic matter. So basically, they incorporate it into their own bodies. And so that's a way that available phosphorus is taken out. But of course, these microbes are going to die, and then they're going to be decomposed back into available phosphorus. So definitely not as complex as a nitrogen cycle. So what we're interested in this agroecology class is how management strategies can actually affect nutrient cycling in soils. So remember, carbon, when we talk about what plants need, there's important cycling of these nutrients and these materials in and out of the system. So carbon comes in via photosynthesis, and it comes out of the system basically by microbes sitting in the soil, eating, the decomposers basically eating the organic matter. So remember, carbon sequestered in the plants via photosynthesis. Plants die, the microbes eat the plants, and as they're eating them, they metabolize the carbon, they burn the carbon for energy. So just like us, microbes eat carbon, they produce energy, and they breathe out CO2. So we breathe out CO2 when we eat stuff with carbon in it, so do plants, and so that CO2 so do microbes, and that CO2 leaves the system. So we already talked a lot about nitrogen and phosphorus, and also, we have to remember micronutrients, but we're not going to talk a lot about them today. Water, how will management strategies affect the amount of water our plants are getting, and but we don't want our plants to get too much water. And again, soil quality, and how might things like pH, salinity, so you don't want your soil too saline, or else it pulls water out of the plants and basically makes your plants shrivel up and die. We talked about pore space, soil moisture, organic matter, and when I say ecology, I mean the microbiology of your soils, so that soil field the soiled food web. So we're going to look at an example here, and I want you to tell me about soil carbon. Remember, soil carbon can vary based on how much oxygen the soil microbes are able to get in order to eat the organic matter and breathe out that CO2. So, the more oxygen that is available in that environment, the faster soil carbon is turned into CO2. Macronutrients, basically nitrogen and phosphorus. Micronutrients, soil moisture, soil quality. I want to know how these two management strategies, conventional and organic no-till, how they affect these basic aspects of the agroecosystem. And so I'll explain that a little further, but the first thing you'll notice is that in the conventional system we're using inorganic fertilizer, so that's fertilizer that's been fixed by the Haber-Bosch process. And in the organic no-till system, we're using manure. So we'll just say cattle manure. So let me just explain a little bit about the differences in fertilization. So inorganic fertilizer is really fast acting. You put it on there, it starts feeding plants right away. But it's also acid forming, and so it contains acidic compounds that acidify the soil. It's cheap. There's greater burn potential. That basically means that there's potassium in there that can end up inhibiting the plant's ability to pull water up if there's too much potassium. So there's greater burn potential. The nitrogen in inorganic fertilizer is easily leached out of the system. So the first heavy rainfall, you're going to end up just leaching a lot of that nitrogen that you applied out of the system if it hasn't been taken up in organic matter already. And with inorganic fertilizer, you also end up with aluminum toxicity, mainly because you start forming an acidic soil, and when you start forming an acidic soil, the aluminum becomes available in the soil matrix, and then plants take up that aluminum, and it accumulates to toxic levels. Now, manure, on the other hand, has a low burn potential, so that's good. You don't have to worry about too much potassium. It's a slow release because there's a lot of organic matter in manure, so it relies on the soil ecosystem to sort of slowly release these nutrients to be available to the system. So manure also contains micronutrients, and so inorganic fertilizers, you can have nitrogen, phosphorus, and potassium, whereas manure is going to have all those yummy micronutrients that plants need. It also conditions the soil. It helps build your organic matter layer, your topsoil layer. But a problem is that it also contains salts, and so if you just keep applying manure, you're going to have issues with saline soils. It's bulky and smelly, costs a lot more per unit nitrogen and phosphorus, so you have to apply a much larger weight of manure than you would inorganic fertilizer. So cows also eat weeds, and so it contains weed seeds, which is going to be bad for trying to keep weeds out of your field. And oftentimes there's way more phosphorus than nitrogen compared to what plants actually need. And so in Amish fields, this is actually a problem because the Amish use manure all the time, and so they have a lot of phosphorus that ends up running off of their fields into the surrounding streams because the plants can't take it up. And that can cause a lot of problems, and you heard a lot about that in Dan's lecture last class. So here's our two management schemes, conventional and organic no-till, and I want you to basically compare these two management schemes. And so like I mentioned, I want you to compare what you would expect to happen to soil carbon, what would be different in soil carbon between these two management regimes, what would be different in macronutrients, basically nitrogen and phosphorus, between these two management regimes? What would be the difference in micronutrients between these two regimes? What would be the difference in soil moisture between these two regimes? And what would be the difference in soil quality between these two management regimes? And so remember, that's going to include things like pH, salinity, soil moisture, organic matter, and soil ecology. And so remember, those microbes are pretty important in the soil, and so for this list of sort of 5 general areas, I want to know the main difference between the conventional management scheme and the organic no-till management scheme. And I should mention that this isn't just over 1 year or 5 years. This is staying in one place on one farm for 50 years, 50 years. And so I want to know the difference in your soil between 50 years of this particular conventional management and this particular organic no-till management. I should mention that there's actually a lot between these two end members, and there's a lot of folks that grow big monocultures that would still be considered in the conventional world that actually use a lot better practices than these. So I don't want you folks to come away with the impression that this is what all conventional agriculture is like, because it's not. There's a lot of great management schemes used in conventional ag. And so I just want you to keep that in mind. These are just end members for the purpose of this activity. So anyway, let me just walk through this quick. So in our conventional ag system, we use inorganic fertilizer, and in our organic system, we use manure. In our conventional system, we use a bunch of tillage and a large amount of heavy vehicle use, whereas in our organic system, organic no-till system, we don't really till at all because it's a no-till system, and there's a medium amount of vehicle use. We still need to drill our seed into the ground, but we don't make as many passes as we do in this conventional system. We have no access to lime, and so lime is ground up limestone. It's usually used if the soil is too acidic. Farmers will apply lime in order to amend that soil. But for this activity, we're going to assume that no lime is available. And of course, in the conventional system, you're using pesticides, herbicides, fungicides, which can affect everything from earthworms all the way down to microbes. And of course, the fungi. And in organic no-till, we're not using any of these. Soil pH is starting out at 5.8, and so you got to wonder what's going to happen to that over the next 50 years. There's a high amount of compaction in the conventional system, soil compaction, or there's a high risk of soil compaction in the conventional system, whereas there's a low risk for soil compaction in the organic no-till system. So let me just make this clear. The degree of compaction between conventional and organic no-till is the same at the beginning of the activity, and I want you to talk about what's going to happen over the next 50 years with this high risk of compaction here versus a low risk of compaction. Irrigation, don't really worry about irrigation. They're both rain-fed systems, but let's assume that they're highly leached. And so this system, let's assume this system is out in, let's see. This system's out in Virginia. And so we've got rain-fed ag, but because of all this rain, we've got the high possibility of leaching happening. And so you folks are going to have to decide if it's going to be an issue in both of these systems, and if so, which one. Planting date, conventional April is sort of the normal time to plant, but because we're using organic no-till over here, we have to wait until we can kill our cover crop, and so we can't plant until June, so that might be an issue. And then, of course, our soil type is clay loam, so it's almost optimal, but a little more clayey than optimal. So I basically want you folks to compare and contrast these two management strategies looking at these, basically comparing and contrasting these 5 major areas, and I want you to be able to write a one-page paper basically describing what's going, the difference between the two management strategies. So that's going to be one page, single-spaced, typed, and that's going to be due. You're just going to bring in a hard copy at the beginning of class on Tuesday, and then we'll move on, and you'll learn more about soil physical structure. So anyway, if you have any questions on this assignment, please don't hesitate to email me, ask me any questions you might need to know. And just compare and contrast this conventional system to this organic no-till system. And remember, you're running it for 50 years. All right. Well, thank you very much, and I'll see you folks on Tuesday for a little bit, and then Ruth will take you for the physical properties.